Hey, welcome back to Math with Patrick. Today is July 24th, and we're solving problem number 205 from the Daily Epsilon calendar. And we need to figure out why this blue angle is supposed to match today's date. We should figure out why x is supposed to be 24 today. So I see we got a circle, and in the circle inscribed we have what looks to me like a regular pentagon, regular just meaning that all of the interior angles are the same. And then inscribed in the same circle, we have a regular triangle, or also known as an equilateral or equiangular triangle. And then ultimately, once we learn some stuff about those polygons, we can do some math with their angles and solve for 24. Now, I could just use the polygon angle sum theorem. Basically, it just states that depending on how many sides you have on your polygon, you can figure out the sum of all the interior angles. So like, for example, with the pentagon, I could just plug in a 5 here, and then that tells me that this right here would just be the sum of all the interior angles. I want to prove this first, or at least, get a nice geometric justification for it before I use it. Then once I am satisfied with my explanation for this, using this will kind of help us figure out some stuff about these angles here. So first off, you and I both need to agree that a circle has 360 degrees when you go all the way around. So therefore, we have 180 degrees, or half of 360, when we traverse a straight line. Next, let's look at triangles, where I'll just draw kind of a random looking triangle right here, and then I'll claim that I can draw a parallel line to the base here. So we both know that a straight line is going to make 180 degrees. So these three angles right here are going to add up together to make 180 degrees. Now, if we do some stuff with parallel lines and transversals, transversal being like another line that crosses a pair of parallel lines, we could also find some congruent angles in our triangle diagram. This angle right here is an alternate interior angle to the other red one. And then this angle right here is another alternate interior pair to the blue angle there. Just to kind of show my thoughts a bit more clearly, they're called alternate just because they're on different sides of my transversal that I'm kind of emboldening right now. And then they're called interior because they're on the inside of my parallel lines. And just one feature about alternate interior angles is that they are always congruent. So if you believe that these three angles form 180 degrees, then you should also believe that the three interior angles of a triangle form 180 degrees when you add them all up. So there's kind of my proof for why we can just assume that any triangle, when you add up the interior angles, gets you 180 degrees. And now let's extend this idea to a pentagon. So here, I just drew a pentagon. There's, 1, 2, 3, 4, 5 sides. And we just saw that when we add up the three interior angles of a triangle, we get 180 degrees. So for all three of these triangles that make up the pentagon, I know that the interior angles are going to sum up to 180 degrees 3 times over, because there's 3 different triangles. And I put little arrows on my kind of angle markers just to show that if we start, say here, on our pentagon, and we traverse all of the angles on our pentagon, we are essentially just traversing all the angles of 3 different triangles. So I could just do 3 times 180 to figure out the total sum of all the angles in my pentagon. And this 3 comes from the fact that there are 3 triangles on the pentagon. And essentially, whenever you draw your polygon like this, you're always going to have 2 fewer triangles than the number of sides. So like if this were a hexagon, I could do that. And then now I have 1, 2, 3, 4, 5, 6 sides. And going from 5 to 6 sides, introduced 1 more triangle. And this pattern is just going to continue for any polygon that you have. So this 5 was because it was a pentagon, and now we could substitute that 5 for an n to be any n-gon that we want. Today, though, we are just doing a pentagon and a triangle, so this generalization doesn't really matter because I proved that all three of these angles add up to 180 already. And then I just proved that all five of these angles, this one on top being all the way across, all five of these angles are going to add up to whatever 180 times 3 is. And that should be 540. That is 540. So we can use this information to figure out what each of the individual angles are. In a triangle, we have 180 degrees shared among three angles, so each of them must be 60 degrees. So we have 60 degrees here, here, and here. Not that the bottom two really matter. And then with 540 degrees, we are sharing them among 5 different angles. And so to do this divide by 5 in my head, I think I'm going to divide by 10 and then multiply by 2. So I'll get whatever twice 54 is, which is 108. So each of the 5 interior angles of the pentagon is going to have a measure of 108 degrees. And this diagram is highly symmetrical. And so I feel like it's fair to assume that this angle on this side is the same as the one on the other side. And so essentially, I have x plus 60 plus x is equal to the whole angle, because I have an x on this side, a 60 across the middle, and then an x on the right side. So now that I've set up an algebra equation, I can kind of ignore the geometry and just solve for x. How about let's subtract 60 from both sides and then collect up our like terms. 2x is equal to 48. And then 2 times something is 48, and that something has to be 24, which matches today's date. So all we really needed was that polygon angle sum formula. And then using it lets us find these numbers. That then lets us find the measures of all of the individual angles. And then finally, we can set up a little algebra problem to find our answer. So that's my solution. I hope you enjoyed, and I'll see you tomorrow. Bye.